Hi, Jeanne, do you mind? I have a few slides to show just before you share.
No problem. Must I stop sharing?
Yes, please.
No problem. Nice to see you, Sula.
I can see you too. Hello, everyone. Welcome. We're starting on the hour, just a few more seconds. We'll allow everyone to come in and settle, and we will be right on our way. Thank you for joining us today. It's definitely a pleasure to have you connect with us, and we hope today's session is as pleasant and as memorable for you. Okay, great. So we're starting. Hi everyone. Thank you once again. Welcome to the May edition of the PhET Africa Share and Discuss webinar series. My name is Shola Olateju, Africa STEM Specialist at PhET Interactive Simulation at the University of Colorado Boulder. Today, we would like to welcome you once again for joining us. We're happy to have you connect again after last week's after our first edition last month, and we're excited as much as you are, and hope you find this session enjoyable. I am not alone on this call. I have with me my colleague and also our very esteemed and special guest who is going to be sharing with us today from our wealth of experience, both as an educator and as a researcher. Rebecca, Zach, and Diana, if you would like to say hello to everyone now, just before we get into the...
Sure. Hi there. Good evening, everyone. My name is Rebecca Vieira. I'm the Associate Director of Global Initiatives. Glad to have you. I'm not sure if I can get our other colleagues on the panelist view at this moment, but I will let you know, Shola. So I'd suggest you just move on for now.
Okay, great. Thank you. Thank you, Rebecca. Thanks, everyone. We also would love to know you. We're going to introduce our guest in a bit, but would love to know you as well. So please write in the chat your name and the country you're joining us from. Write in the chat your name and the country you're joining us from. This session is recorded and will be made available to, of course, at the end of the session for registrants. We also have our guest, like I said, we're going to introduce shortly. So just give us as we go through a few things. But for those who are joining us for the first time, this webinar is brought to you by PhET Interactive Simulation at the University of Colorado Boulder. PhET was founded in 2002 by the Nobel Laureate winner Carl Wyman. The PhET Interactive Simulation project creates free interactive math and science simulation. PhET teams are based on extensive education research and engage students through an intuitive game-like environment where students learn through exploration and discovery. They emphasize making connection between real-life phenomena and the underlying science, and help make the visual concept and help make visual and conceptual model of microscientific concept accessible to students. The Africa Share and Discuss series, which is why we are here today, brings us together every third Wednesdays of the month, through which we bring together educators and researchers alike to present evidence-based teaching strategies to make more effective, to improve and ensure, of course, teaching of maths and science become effective using PhET teams. We're going to take a few housekeeping rules before I introduce our guest. We would like to welcome everyone. This session, of course, we have people joining us on Facebook and on Twitter. So please, if you have questions, we've saved enough questions for interactive. We have some time at the end of the session, so we will not allow session while the presenter is speaking, but we've saved time at the end so that you can ask your questions. But while at that, please, you can write your questions in the chat or use the Q&A function if you're connecting via Zoom. So write in the chat there on Facebook if you're connecting via Facebook, or write using the Q&A function here in Zoom. The conversation does not end here, it only starts here. So we encourage that you also join the community on Facebook, which is at the link below. If you search for PhET Educator Africa, it will take you to the group where, of course, conversations like this can continue beyond the limited time we have today. So I'm going to introduce our guest now. Today we have the pleasure of having Professor Jeanne Kriek with us. Professor Jeanne is a researcher in physics education and a full professor at the University of South Africa. Our research interests are in teaching and learning in physics with the use of technology, nuclear energy, and professional development. She's used PhET since about 2002, 2003, when it was still being distributed via CDs, and has published over 12 articles. So she brings a wealth of experience both from classroom use and well as research. Today she's going to be sharing with us on effective strategies for teaching with PhET sim. I'm going to hand control over to Professor Jeanne now. She presents, of course, introduces some of the things she's learned from her research, but also some of the strategies that she's found effective. And we'll come back to questions at the end of the day. So please remember to write your questions in the chat. The team and myself is aggregating them, and at the end of our presentation, we'll bring them all and spend some time to address it. Thank you for joining us, Professor Jeanne. Over to you. I'm going to stop sharing now, and I'm sure you have your slide to share.
Good afternoon. Okay, you're still there. Sorry, can you see my slides?
No, not at the moment. It came up briefly and it went down again.
I think I'm out. I'm going to leave.
Okay, while we're waiting for the speaker to come up, I'm sure some of us have tried or employed different strategies in our use of PhET, or of course driving and supporting inquiry and active learning strategies in our classroom. Please, if you have some questions, you can drop them in the chat, and of course we're going to also take that as we wait for the speaker to come on. So please drop them in the chat. She's back now.
I'm back.
Okay, great. The screen is on now. Your slide is on.
Okay, good evening, colleagues. I'm very privileged to be invited to present this webinar. Thank you for this opportunity. I'm coming from a research background, but try to share the research that has been done so practical as possible. Research informs teaching. If there was no research, no new teaching strategies would have been invented, and we would have continued teaching using chalk and talk. So all of you are familiar with PhET simulations. My talk is on the pedagogical effective use of simulations in STEM. So how do I know that PhET simulations are effective? The only way how I know that is if I can develop conceptual understanding, because the ultimate goal of teaching is to promote learning. So conceptual understanding is I just want to take this away. is a capability to reason in settings, environments that require careful application of concepts, descriptions, relationships, and representations. Conceptual understanding is something robots cannot do. Robots can replace the way information is taught or how basic tasks are performed, but creativity, experience, and underlying structures may not be as replaceable. Therefore, you always have to ensure that there's conceptual understanding taking place whenever you use PhET simulations. Why is it important to facilitate conceptual understanding? You can assist students to make connections, develop metacognition, and I'm not sure if all of you know what metacognition is. It refers to higher order thinking involving control over the thinking process. And it says you have to assist students to transfer knowledge to new situations they encounter. And how do we ensure that students develop conceptual understanding? And you have to use diverse methods in teaching. And I would like to share with you a few teaching strategies using PhET simulations. The first one is demonstration, and then conceptual change activities, cognitive perturbation and cognitive conflict, virtual laboratories, and inquiry-based learning. So let's start with the first one. Demonstration teaching strategy. This is especially useful in overcrowded classrooms. I think all of you know how to use it. There's a teacher and it connects his or her laptop to a projector and show the PhET simulations on a screen. It's not necessary to have a screen. You can do it on the wall as well. It's used in the absence of resources, and normally you must please use the predict, observe, and explain strategy. I'm going to explain it to you now. Predict is you ask the students what they think will happen if you give them a question or an idea. But make sure that the students commit an answer. Observe is when the teacher demonstrates what is happening, and explain is what I think is the reasoning behind what they see. And please remember, you must not forget to give feedback at the end of the class to empower the students to know the reasoning behind what happened in the experiment. This is extremely, extremely, extremely important. In the next teaching strategy, let's look at conceptual change activities. This is a learning process. Conceptual change is a learning process in which students' alternative conceptions or misconceptions transform or are reconstructed into the intended scientific conceptions. So it is a learning process that you have to go through. But there's also a conceptual change model, and this model has 6 stages. The first stage is you have to commit to position or outcome. The second one is you have to expose the beliefs. Then you have to confront the beliefs, accommodate the concept in that phase, extend the concept, and go beyond the phase. And I want to explain each of these stages to you. In the first stage is commit to a position or outcome. Ask a question or present a problem or challenge. The students then realize their own preconception, need to formulate their answers or solutions to become familiar with their views. And at this stage, the teacher does not comment on the students' responses. The next stage, I'm going to explain this. I'm just going through the slides now. And in the next section, I'm going to show you how to apply these strategies. Share and discuss ideas in the second stage. The predictions and reasoning with classmates. That is the reason why you have to commit yourself. Teacher classifies student responses into categories and a whole class discussion follows. This discussion gives students the opportunity to change their initial beliefs, and the teacher does not comment on students' responses. The next stage is you have to provide experiences that challenge the students' preconceptions. Students interpret the outcome of the experience. The teacher provides technical assistance to the students, and students in most cases become dissatisfied with the existing ideas. The difference between what they were expecting and what they actually see provides an opportunity to develop the scientific model. The fourth stage is the accommodative stage to this new view by summarizing, discussing, debating, incorporating new information. The student who understand the concept explain their views to their classmates, and this we also called peer teaching. This is a very good strategy because it's always good to have a good student explaining to his fellow students if he understands the concept better. It helps the specific student as well as the others who do not understand. The good student benefit from expressing how he understands the situation, and the poorer student understand it better in this stage. So this is a very good way of a strategy to use in your classroom. Normally the student accommodate the new concept, and in this stage the teacher assists in drawing conclusions and formulate principles relating to this newly acquired information. Stage 5 is the apply and make connections, and these situations may be presented by the teacher or fellow classmates or by themselves. Okay, and then the go beyond phase is students pose or pursue new questions, seek additional situations where acquired concepts or skills can put into practice, and discover new situations. Okay, now let's start. Now we're going to apply what we just said in the 6 stages. So each of you have to think, and you're going to have to commit to an answer because I'm going to ask you what your answer is. So compare the brightness of bulbs A, B, and C in these circuits. Which bulb or bulbs are the brightest? Is it A? Is it B? Is it C? Is it A and B? Or is it A and C? Please take a few moments and decide. So you have to commit which of these, which ones are the brightest. Okay, I want you to raise your hands. Who says A? So you can please just show by using your hands. And can you put up your hands in Zoom? I think you can. Sola?
Yes, about two to three participants raised their hand for the first, for A.
Okay, and for B?
There are no hands raised yet.
Okay. Sure, they're not committing their own to answer. And then C?
There are about 5 already raised. We have 7, 8 participants.
Okay,
So we have 9 hands raised.
Okay, great. And who says D? Sula, can you say?
Yes, there are about seven hands were raised, but there are all 6 hands were raised. So for the first we had 3, for A we had 3, for B we had none, for C we had 9, for D we had 6.
Okay, and E?
Okay, so if we have more hands raised now, so we have about 10 hands, we have 11 hands raised.
For E?
Yes.
Okay. Okay, so all of you have committed yourself to an answer. So the next stage is we have to expose our beliefs. So let's see what happens. Why doesn't one go on? Okay, so now you draw the circuit. The first one is the battery with one bulb. And in the second one, it is the battery with two bulbs. Can you see that it's A and C, that it has got the same brightness? And now we have to indicate why is this so, because the current this is the same current flowing with one battery. And yeah, it's the same current flowing with one battery because the current takes the shortest distance between it. So the teacher helps them draw conclusions and formulate principles relating to the new required information. So what we have to say is that it is A and C has got the same brightness, and brightness are normally calculated by power, using the power, and this is the formulas that you use to calculate the brightness in the bulbs. Okay, but now we have to extend and go beyond what we've just done, and we have to apply it to a new situation. So I would like us to please read through this one, and you have to commit yourself to an answer here as well. What happens to the brightness of bulbs A and B when the switch is closed? Does A stays the same and B dims? Is A brighter and B dims? Is A and B increase? A and B decrease if it's closed? A and B remains the same. Okay, can you please commit to an answer? I'm going to leave it a few moments so that you can just work it out for yourselves. Okay, Sula, can you please raise your hands? Who says A?
It looks like we've got about 4 or 5 hands. 4. Somebody just put one down. 4 hands.
Okay, and B?
Let's give people a moment. 1, 2, 3, 4, 5, 6, 7, 8. About 8 people. 9.
Okay, and C?
Let's take a look. I'm seeing 3 hands at the moment.
Okay, and D?
Let's give people a moment. I'm seeing 2 hands, 3 hands.
Okay, and E?
One moment. I'm seeing 4 hands.
Okay, so that is the first stage, that you have to commit yourself. Now we have to expose your beliefs, what you were thinking. So we're going to confront it. So we are drawing this circuit. There are the bulb and the switch is open. And there's the other bulb. I think this is A and this is B and this is C. I think so. So A and C is the same brightness. Is that right? But the moment when we close the circuit, what happens? A becomes brighter and B and C has got the same brightness. Can you see that? Okay, but now we have to accommodate. So we have A is brighter and B dims. We have to indicate why. And then remember, always ask the student to explain what was happening so that they can accommodate the new understanding. And this can be done in groups or whole class discussions. And remember, if your one student understand it better than the others, he can also help in explaining this to his fellow classmates. Okay, now I want to go to another alternative teaching strategy that has been used, which are, in any case, the first one is the cognitive perturbation strategy and cognitive conflict strategy. We are also going to do examples here. So cognitive perturbation and cognitive conflict. Cognitive perturbation approach involves a step-by-step learning of concepts based on the understanding that paths of conceptual change for different students, groups of students, are idiocentric, idiosyncratic, diverse, and context sensitive. So you will not give the same approach perhaps in Ethiopia than you will have in South Africa. So you must make sure that it's a context sensitive as well. And cognitive conflict is a strategy in making learners dissatisfied with the existing alternative conception and making the scientific conceptions intelligible, plausible, and fruitful. I'm going to give examples of this as well. So with a cognitive perturbation strategy, the students are gradually provided appropriate perturbation from their preconceptions, what they have, towards scientifically more viable intermediate conceptions before they are guided to scientific conceptions. I'm going to show you how. We have a garden house, and this was previously cut at its center and has been repaired by splicing a short length of house with a smaller diameter into the break, as indicated in the diagram. When the house carries water, the speed in the small middle section of the repaired house at point B compared to the speed at point A is higher, lower, or the same. Please think. You don't have to tell me, so please think. Will it be higher, or will it be lower, or will it be the same? Okay, can we please have a raise of hands again? Who says higher? The speed would be higher, the repaired house B compared to the speed at point A. So will B be higher than A?
I'm seeing, I think it's about 10 hands.
Say it will be higher. Okay, and who says it will be lower? How many hands?
It will be higher.
I'm seeing
No.
5 hands now.
And who says it will be the same?
Let's give people a moment. I'm seeing about 7 hands. So not everybody's voting.
No, so let's start again. They must vote. Otherwise, I know they're sleeping.
We
So
have
who
a lot of people are also responding in the chat, and it looks like actually all of the responses in the chat are A.
Okay, so if you look now, because it's cognitive perturbation, there can be an intermediate understanding question. So what happens to the water in the pipe at the outlet if you halve the outlet by using your finger? And this can help you to decide that what the answer is. So let's do the question. So this is the pipe, and I've decreased the area where it flows through, and there the speed are. So the speed is higher in B compared to in A. Okay, now we have to extend this the equation of continuity. So we have to say what the answer is, and also why did you get that. So if A is smaller, if this is smaller, V2 will be bigger in the end. Okay, so let's have another example. When the house carries water, the pressure in the small middle section of the repaired house at B compared to the pressure at point A. What will the pressure be now?
How many say A, higher? I'm seeing 4 hands so far. 5 hands.
Okay, and how many say lower?
The pressure will be the same.
Pardon?
I'm seeing 3 hands.
And the same?
4, 5, 6 hands for this.
Okay. Okay, so why do fluids exert pressure? That's the intermediate question. And fluid exerts pressure in all directions because the particles in the fluid can move in all directions. So the movement of these molecules results in continuous collisions, and the collision causes pressure, which is exerted in all directions. So what does that mean? So the pressure, when the volume is bigger, is higher compared to when it is smaller. And this is the higher the velocity in a fluid, liquid or gas, the lower is the pressure. And this is because of Bernoulli's principle. So fluid pressure is caused by the random motion of fluid molecules. When the fluid speeds up, some of the energy from that random motion is used to move faster in the fluid's direction of motion. This results in lower pressure. And then you can explain it by using Bernoulli's equation and the volume, and you can answer the questions using this formula. So in this cognitive perturbation, the students are constantly challenged by the teacher with questions, which were based on the explanations of concepts in the interactive simulations. Cognitive perturbation would help the students learning towards the forming of intermediate and more scientific conceptions than their preconceptions. And then you start, and then it goes on. So the difference between cognitive perturbation and cognitive conflict is that the cognitive conflict strategy starts with a conflict and then rejects alternative conceptions. I'll show you now. So the intention of cognitive conflict is to create cognitive conflict in the students and make them dissatisfied with the alternative conceptions and increase the status of the scientific concepts. So let's see. Yeah, I indicate the pressure is higher in A compared to B. So I give this could be a conflict because the student can think the other way around. And then what is even worse, if you say there's a bigger pressure, if you look at pressure equals force times area, here you would say if the area is bigger, the force would be smaller. And this is not happening in fluids. So this is a conflict. So this discrepancy between predictions and outcomes create cognitive conflict and students and provide contradiction. So the teacher needs to guide the students to abandon their alternative conception and replace them with scientific conceptions. So this is the difference. The difference is you give the statement, you say the pressure is higher in A compared to B, and cognitive perturbation, you say, can you explain the difference in pressures A and B? And yeah, you help them with leading questions to get into an intermediate phase, and then you use it to the final phase, the scientific acceptable phase. And quickly just going to look at laboratories, traditional animation-based, simulation-based, remote triggered labs. I'm just quickly going and glance over them. Traditional, we all know that the advantage is it face-to-face. The disadvantage mainly is that you have to schedule lab hours. Animation is easy access to labs, but it's close proximity to real lab scenarios, and it's also the disadvantage is they always have ideal results. If you compare it with the simulation-based labs, it's also it's a high degree of interactivity, but you can also change the variables which represent real data, which makes it very, very nice to use. But you have to understand how to work the simulations before you can just use it. And then this remote triggered lab is when you have, for instance, in the States, the doctors are doing an operation in South Africa, for instance. So the instruments are very expensive and you always need network. So there can't be network related issues if you do operation of that nature. So virtual laboratories, which is good in PhET simulations, you can explain the microscopic aspects. You don't have a fear of damaging the apparatus. Try the experiments virtually before that. Use it as pre-lab sessions. Please always use the specific predict, explain, and predict, observe, explain protocol. And always remember not to leave the students in the middle. You have to explain what the correct way is. And can replace a physical laboratory when schools do not have well-furnished laboratories. But I'll show you what research we have done on this. We did a research study among first-year physics students at a university on electric circuits. And we wanted to find out which of these approaches are the best to use. Must you only use traditional apparatus, or do you only use simulations? And the one group only used traditional and simulations together. And we wanted to find out which one of these approaches are the most effective. The simulations outperformed the traditional laboratories, but the simulations and the traditional combined outperformed the simulations only. So it's better to use traditional and PhET simulations simultaneously in higher education at university. So that was the one study. And then another study in inquiry-based learning. Sula said you did a few webinars on inquiry-based learning. There are 4 types: confirmation, structured, guided, and open inquiry. So I'm just going to talk about the last 2. In our study, we looked at these 3 pedagogies, and we wanted to find out which of these are the most effective to improve grade 12 learners' understanding of the photoelectric effect. The 3 was chalk and talk. The other one was guided learning with computer simulations as a demonstration tool. And the last one was semi-autonomous learning, where the learners used computer simulations individually with limited support. And it was quite interesting what the findings were. In guided inquiry, the teacher plans the activity and students explore a phenomena or idea. And from this, the teacher guides them to develop the desired science concept. Our study was a little bit different. The teacher manipulated the computer simulations, demonstrating phenomena and asking guided questions, which is referred as guided learning. In open inquiry, students explore a phenomena on their own, devising ways of doing so with minimum guidance, after which they report what they did find. In our study, the teacher offered guidance by being available for questions, providing notes and instructions sheets to help the learners when using the simulations. This is not exactly the same as that they have to do it completely on their own. They did have a little bit of guidance. So we called it semi-autonomous learning because it wasn't exactly open inquiry. And the findings was very interesting. The significant effect on the instructional group favoring the guided learning experimental group. What was interesting is that even the group subjected to chalk and talk had better results compared to the semi-autonomous learning group. That was very interesting for us. And therefore, it suggested that guided learning, where the teacher manipulates the computer simulations, is a better method for effective teaching of the photoelectric effect. So the demonstration tool that strategy that I described in the first place is always a good strategy if you don't have any equipment. So please just don't throw that away. So I did an overview of these teaching strategies, and this is my website. If you want to look at my publications, I've supervised 17 masters and 12 PhDs to completion, and that is my email. So you're more than welcome to contact me, and thank you. It was wonderful to do this. Thank you very much, Sola.
Thank you so much, Professor Jeanne. Thank you for sharing as in so much in so little time. I'm sure we've had a lot of some new concepts to pick up from this, and I particularly enjoyed the very practical carrying everyone approach. I would encourage everyone to use the question and answer function to drop their questions at this point so that we can get to them. We would endeavor to cover as many questions as time permits us. So this is a very good time to drop your questions. I'm going to take the first few questions now. This is Alie Zanionisa. Thanks, Prof. Kriek, for sharing your research. How and to what degree was the CS manipulated? Zanioli, would you like to speak or share more detail about your question? To what degree was the CS manipulated? The next question, we'll come back to that in a bit. Will the slide be shared? Yes, we'll share the slide with everyone after the session. We'll communicate how to get access to that. While we're waiting for more questions to come through, I have a question which might seem very basic. We'll just take us back to the very beginning, and it's around the predict, observe, and share. One of the things we've noticed from inception are teachers are of course excited about using the SIM, but often we realize they in certain scenarios still take ownership, in which they are the ones demonstrating, as in showing how to use it, as against using this method, or in scenarios where of course devices are in abundance or deficient, students should have the chance to explore themselves. In your experience, how do you encourage your students and peers to stay true to some of these strategies, to avoid the urge of trying to take ownership or being at the center of the class, basically the whole active strategies? How do you advise educators to put all of these strategies to remember them and endeavor to put them to use without fear? I know it can be tricky at times, but what are your advice or strategies to ensure that?
I would really recommend if you have a lot of if all the PhET simulations can be downloaded on a computer and each of the students in the class have access to PhET simulations, obviously that would be the best. But I really encourage you to be interactive. You must ask questions that will let them think. Although they must have the opportunity to play around with the simulations themselves, they can download it and do it at home, for instance, and just enjoy playing with it. But I would suggest that in class time, you have to structure questions that will make them think. Otherwise, there's actually no, it's a very wonderful thing to play with it and see what the outcome is and how the brightness will change. But in the end, the class time must be structured in such a way that the students learn conceptually.
Okay, great. Thank you so much. Zach, can you go with your question now? And I'm going to also take the next questions in the chat. So over to you, Zach.
Yeah, thank you so much, Prof, for that insightful presentation, especially the diverse teaching strategies that you've shared, particularly the way you use concept questions by just presenting to learners and allowing them to discuss and then having a vote and then doing a demonstration. So my question is, as a teacher, how do I write a concept check question so that, you know, it really motivates the learners to be able to engage with the question itself and be eager to find solutions to it?
Okay, Zach, I'm not sure if you are familiar with physics education research. There are a lot of questionnaires that you can have access to. I don't know if you know them, and it's always good to look at those kind of questions and give that specifically to the students before, you know, because I think there's been a lot of research in all of those questionnaires. So I would really encourage all the participants to look at those questions whenever you start, like geometrical optics, for instance. Then you look at that specific questions that they have and incorporate that. You can have clicker questions, you can have raising hands in the classroom. So it's not necessary to have all that technology. But that is very, very important to have this leading question that really makes them think.
Great, thank you. And yeah, my last question is, what really makes PhET simulations particularly useful to use with the strategies that you've just shared with us?
I think the fact that it's so easy, it's so visual. You can see the elements and you can see what happens on a very interesting way. So, I mean, some of my students looked at the various other simulations that would be more useful, say, for instance, in potential, electrical potential. But in the end, we always use the PhET simulations as well, because it's simple and very visible.
Great, thank you. Back to you, Shala.
Okay, great. Thank you, Zach. We have a few set of questions that, yeah, we'll try to cover them. One of them is, thank you for sharing with us. Please help us biology and chemistry teachers. But the question is, how do we put into the simulation class for 40 minutes? I've tried this several times and failed time management. There's usually the conflict in balancing this methods or strategies within the time constraint. What advice do you have for the teachers?
I would really ask difficult questions in the beginning so that all the learners, if you start a new section in chemistry, for instance, start with a really difficult question and then go to the simulations to try and find out the solution of it. You can only use 5 or 10 minutes in doing the experiment rather than taking the whole time for class, because I have to practice it as well. So that would be my strategy. Just in the beginning, ask a few questions, show them the answers, and then they have to explore and explain.
Okay, thank you so much for that. Another question from Adam Reynolds reads, say you need to adapt the recommended practices you described to be done without a teacher. For example, with a guided worksheet with learners on their own at home. Are there any specific ways that these strategies need to be changed or pitfalls we need to be aware of when exposing learners to cognitive conflict when we are not there in person to resolve it?
We really found that if they work on their own, they really have a lot of problems in there's numerous of problems. So the final was to use guided learning. But if you prefer to do it on your own, that's quite fine. But try and get questions like I asked, like the hose pipe, where you have these intermediate questions so that they can think about that before they go on and not understand what to do in the next in the next stage. So those in-between questions, I really think it helps a lot. And you have to have reference of where they can find answers of that in-between questions, so that lead them to the following. So they're not in the, yeah.
Okay, great. Thank you. So there are comments here. Someone is thanking you here for, of course, for a great presentation, and said she likes the predict, observe, and explain method you described. And there's another one, which I think is basic, but like one of the most very critical question. Can you engage students to interact with simulations without the questions?
You mean the leading questions in the beginning? Is that what I mean?
Yeah, like I would assume questions generally. I don't know, explore without questions. Just your thought on that?
I'm not part of, I don't like that, because students come to the classroom and they think about what happened last night and what they're going to do tomorrow or this afternoon or whatever. You have to get them focused. And if you have this brilliant question that they really have to think, and they have to commit themselves to a question. It could be some kind of experiment. It's not necessary to be a question, but you have to have something in the beginning that will really ignite their thoughts. They must think of what's going on in class.
Okay, great. Thank you for that. I think this would be a good time to add that you should look out for an announcement in coming weeks. We're also going to share information about a virtual workshop that can help you continue to learn about some of the concepts that you've learned today. I would advise that you stay in touch or connect via Facebook, join the community there so that you can get information as they become available. And once the announcement is made or access is made available, definitely we will share across the network and keep you informed. In subsequent editions as well, once the announcement is made, I'll be sure to let you know so that we all do not miss out on that. Thank you, Professor Jeanne. We still have a few minutes, so we can still take some questions. And Adegboyega Adedinri is asking, thank you for your presentation. The cognitive conflict scenario might have more than one correct answers. What should I do about this?
Do you mean that the intermediate questions that that's going to ask?
Yes, I'll go through that again. It's more the cognitive conflict scenario might have more than one correct answer. If there are more than one correct answer, how do you manage such scenarios?
I think the most important is to have the one that the people would not think is the correct answer. I think that's always the best strategy, to take something that they really would think that it's going to be in this direction, and then you come up with completely something different, and that makes them think. So I know there's a lot of answers that would be correct, but choose the one that you think that nobody will think of.
Okay, thank you so much. We have time for about one or two more questions. If you still have one more before we send our appreciation to Professor John. I think we have just one more, and this is coming from Abdul Ok Suleiman. I think I can take this. Are there worksheets on practicals for teachers to use? Yes, alongside the simulations, if you go to the simulation page on the PhET website, you're going to find activity sheet that you can adapt or use in your classroom. Some of them have been designed in line with some of the things discussed today, and many of the strategies that PhET encourages as well, which I mentioned you would learn more about when we announce the course in coming weeks. So there are activity sheets that you can use, but also we have something called the teacher tips, and the teacher tips basically helps you understand some of the design principles, some of the things to consider, then some of the learning goals and some of the things you can consider. So once you go to the page, just look out for the tabs beneath the image of the scene. You'll find different information about that, one of which are the worksheets for teachers to use. Because of our time, we would have to draw the curtain here. I would like to first appreciate Professor Jeanne for our time and sharing. It's always a pleasure to have you and of course connect and share from your experience. Of course, and thank you for sharing. And of course, we're excited to continue to have you connect with the community. And of course, once the opportunity or other information become available, definitely will be a pleasure to have you join us and also connect even when you're not speaking. Thank you so much for joining. So we'll start wrapping up now, so that there are a few more things to do. If you still have a few questions, we might be able to take one or two more, if we can squeeze that in. But at this time, I'm going to take time to appreciate everyone who have joined us today. Also, then talk about. I'm going to share my screen if you don't mind. I'll just take a minute. Okay, great. So yes, we've come to the end of the May edition of the Africa Share and Discuss webinar series. It's the first in the series, and we intend to have this continue to run, to ensure that you continue to connect with the community, learn about effective strategies such as this and some of the other information that would help you effectively leverage some of the tools that are increasingly that we continue to release from PhET. Please connect with us, and please connect with us. You can find us by visiting our website, phet.colorado.edu, phet.colorado.edu. We also encourage that you use the SIM in the classroom. We encourage that you use the SIM in the classroom as a teacher PD, or just leverage it in the best way possible. There are also other opportunities that you can support and contribute to. Become a supporter of PhET. Of course, you can donate, but beyond donating, alongside that, we also make available these resources in African languages, so you can create teacher resources and share with the community. Alongside some of the things you've learned up today or activities that you think would be useful. Once you've created them, you are able to share and let other teachers access them. So we encourage that you contribute in that, or if you are competent in any of the African languages, we are actively translating more resources into African languages. So there are opportunities to contribute alongside using class, but also ensure there are scaffolds and tools to ensure this pool of resources basically is accessible and unlocks opportunity even in more community, and can get more students who might be cut off at different points. And finally, you can connect with us on Twitter at PhETSIMS and on Facebook, and I mentioned already the group on Facebook. Next month, we're going to be having another interesting conversation where we're going to discuss students' perception and attitudes towards simulation. We're going to have Ms. Mafo Penn. She's a science education lecturer and researcher at the University of Johannesburg, where she's going to share some of our research as well, some of our research findings, but also shed some light into discussing students' belief, their preferred roles, and common actions, the things they do, what they often look out for, and how they feel or react during simulation use. We're going to look at that so we can build on our knowledge. As the more we learn about the design principles, we learn about how effective strategies. We're also going to learn about insight into how to understand and support our students in a sim-based when we're using the sim in our classrooms. I would also advise that, of course, we're also open if you have things you would like to learn on this platform, things you think we should consider in future editions. Please feel free to reach out to us and connect with the team, and we'll be sure to consider that as we design and bring to you the next set of speakers and conversation. Thank you so much for joining us today. I would allow other members of the team say their byes as we draw it to a close. Rebecca, Zach, are you still there?
I am still here.
Cool.
And Zach and I have to pop off in just a minute to go meet with our fabulous group of PhET fellows from Africa. I know there are many of them here. Would they like to raise their hand real quick, just so that we can see who's here? I know Rita was here. Richard H. Bonney is here. Godfrey Odiambo, Tuaya Manyozo. Let's see here. Offense. Fabulous. So we've got a good group of fellows. Anyway, we've got to get going ourselves. But thank you, Shola, and thank you so much to our speaker, Professor Jeanne Kriek. And Zach, anything you want to say?
Thank you, Prof, for the wonderful insights. Thank you.
Okay, great. Thanks, everyone. We're going to draw the curtain here and look forward to having you again next month. Enjoy the rest of your day. Thank you.
Thank you very much. Bye-bye.
Bye.